Hello and welcome to another video. In this video we're going to be looking at largest local values in a matrix. And this one we're given an n by n integer matrix grid, and you want to create a matrix of size n-2 such that max local ij is equal to the largest value of a 3 by 3 matrix in a grid centered around row i+1 and column j+1. In other words, you want to find the largest value in every contiguous 3 by 3 matrix in a grid. So basically kind of what they mean is whenever you have a matrix, so you can picture that like you make a submatrix where you're not including this outer section here. So this whole outer border. So this represents this section here. And then for each of these values, so this value represents this thing. And you're basically asked for this value, give me the largest value in this 3 by 3 section around it. So around this whole thing. So the largest value here would be a 9, and this represents this, and the largest value here, right, this whole 3 by 3 section is a 9 as well, and then here, this is this, so this whole 3 by 3 grid is an 8, and here the whole 3 by 3 grid is a 6. Same thing again here. Basically this inner matrix is this thing here, represents that, so not including this. This is where this inner matrix would go, right in the middle. And so this represents this cell. And I think it makes it easier if you just like draw, like this matrix represents this section here. And so now you know like what cell corresponds to what. And basically here we want the biggest number in this 3 by 3, which is a 2. Here it's a 2 as well. Here it's a 2 as well, so these should all be 2s. Then now for the next row, it's going to be this is a 2. The middle one has a 2 already. This has a 2 as well. This has a 2 as well. And this has a 2 as well. And this has a 2 as well. So you just return all 2s. So basically, kind of like what you're roughly trying to do is you're trying to say, okay, I have a matrix and I have a submatrix. And what, like, you have to recognize like what, like, let's say this is at 0, 0. Where does that represent my original matrix? So 0, 0 actually represents being at 1, 1 in my original matrix, right? This cell here. Then this represents 1, 2, and then and so on. So this will be 1, 3, and then 2, 1, 2, 2. Yeah, so 2, 3, 3, 1. 3, 2, 3, 3. And if you look, like 1, 1, where's 1, 1? So that represents a cell. This is 1, 2, and so on. So this matrix would go right in here. And then basically all we need to do is for a particular cell, so let's say we're at 0, 0, we just need to say, okay, this represents this location in the outer matrix, or in the outer grid. Then we just need these 9 numbers. So for these 9 numbers, it's pretty easy. Like let's say we're at 1, 1 here. We can just have a for loop that checks every single combination of row and column that's either 1 greater, right? Because 1 greater would be like the next thing, or 1 less, or the same. So basically all combinations of row and column from -1 to 1, -1 to 1. And then that way, if like, let's say they were both -1, from here, if you both go to -1, so you would subtract 1 from each, so that would be up here. Then this one would be the row being subtracted by 1, the column being the same. This is the row adding 1 and the column adding 1. This is the row being the same and the column adding 1. Actually, sorry, this one would have been the row subtracting 1, the column adding 1. This one's the same, the column adding 1. So we can even say this. So we can say like this is 0. We can even show like how to get to all these cells. So this is subtracting 1 from both. So -1, -1. This is subtracting 1 from the row, the column being the same. This is like if this was 0, 0 essentially. But you basically take these values and you modify them by these 2 to get this. So here, this would be the row subtracting 1, the column adding 1. Here, the row is the same, column adding 1. Here, you add 1 to both. Here, the row is increased, the column stays the same. Row is increased, column decreased. Row is the same. So you can basically see that you have all combinations of numbers from here to here. And then once you have this thing, like let's say my current row is 1 and my column is 1, then I just pick one of these to go to, and I have to check all of them. So like let's say I pick this one, then my row would be the same. I'd subtract 1 from the column, so I'd check like this location. But basically, for every cell, you just map it to where it starts in the grid, and then you just check all 9 of these numbers. So essentially, the time complexity here would be something like n squared times 9, because you check everything else. And I did show this again, kind of just to show this really quick. So this big grid, even though it looks really big, is still the same thing. Like this big grid represents the inner region of this. So not counting these cells. So like if I make an outline of this grid, like where would this go? In the big grid, it would be right here, right in the middle. And this cell is the same as this cell. So once again, this 0, 0 is 1, 1. This 1, 1 is 2, 2, and so on. So the transition from the smaller grid to the bigger grid is just add 1 to the row in the column. And that's the center. And then basically you're saying now your problem is like, given a cell in a grid, get the biggest value for that cell and all the cells around it. And like I said, you can just loop row and column from these values and add it to your current cell. So the cell would be at like 1, 1 and so on. So that's basically what we're going to do. So we're just going to make a new grid, loop through our original grid for every single one of these values. You can do some optimization maybe to save some values, I guess. But there's kind of no need, because it's only 9. Because yeah, there is some like overlap. Like for example, when you calculate this cell, you get all of these. So when you calculate like this cell, you're still doing a lot of the same work, but you're getting only these now. But because it's only 9, it doesn't matter. Like if you were getting some huge matrix, that's when you would be doing some optimizations. And that's why this is an easy problem. So just the main thing to visualize this goes in here and how it correlates to it. So we can code that. So first we'll make our result matrix. That's going to be, so first actually let's get the length of the grid. So we'll say n equals grid length. Then we're going to make a result matrix. That's going to be n minus 2 row length and n minus 2 column length. So we can say int result equals new int array. That's n minus 2 and n minus 2. Then basically all we need to do now is we need to loop through our new matrix and then know where that corresponds to in the grid, and then check all 9 of those locations. So it'll be basically just 4 loops. So we can say for int row equals 0, row is less than n minus 2. So this is the dimensions of our result. Then the same thing for the column. So remember, we start like, if we're at row column in the result, then we're at row plus 1 and column plus 1 in our original grid, right? This corresponds to this. So we need 2 more loops. So we'll say for int I equals -1. So we need to go from -1 to 1. So I is less than or equal to -1. Or not -1, 1, I plus plus. And same thing for the other one. 1. So we basically just need to take, so our result values are going to be initialized to zeros, and every value in the grid is 0 or more. I think it's more than 0. So we can just take our result and say that the result is equal to the greater value of the result and the current value in the grid we're looking at. So we could say result equals the max of our current result. So we actually need this cell. So this is the cell in our result, so in here. So this is going to be our old value. And now we need to basically say like, okay, for these 2 values of I and j, where does this correspond to in the grid? So this will be grid. So remember, the row and the column in the result corresponds to row plus 1 and column plus 1 in the grid. But now we also need to add these I and j values. So we're going to add I to the row, and we're going to add j to the column, and that'll give us all combinations of cells starting, like if we were at this cell in the grid, that's all combinations of these, all 9, because it's 3 by 3 here. And yeah, that's basically all we need to know. So as long as you can like visualize what's going on here, that's basically all you need. So let's just return result. Don't need to debug. Okay. And yeah, so basically all there is to that. I don't know how you can make it more efficient, but I guess it's like kind of close to MS4MS or whatever. So I don't think there's a big deal there. Oh yeah, like I said, you can, and actually I would know how to make it more efficient. So you can make it more efficient by not doing duplicate work, but because the dimensions are so small and it's an easy problem and there's only 9 places you have to check, I think this is like the easier way to do it. You can think of like, okay, how would I not do duplicate work? And there's a way to do that, like I said, because when you check a cell, you're doing repeated work, right? So if we just say like, for example, like let's say we check this cell. To check this cell, we check all of these. And then when we check this cell, we would check all of these again and all of these. So there's a way to like minimize that. But yeah, for an easy problem, I don't think it's worth going into. So this one will be time of n squared times 9 because you're basically checking 9 locations. And space, this will be O1 because you have to make the result like this doesn't count for the space and we don't use anything else. So hopefully this is helpful. If it was, please like the video and subscribe to the channel. If you have any questions, as always, write in the comments, and thanks for watching.